Hello. We're going to look quickly at a couple of sections here. 6.5, length of curves, and 6.7, which is some applications, basically, of some of the integration that we've been doing in this chapter. So, for length of curves, they do a derivation here, kind of at the beginning of the section. And, hey, this looks pretty similar. What we're going to look at is, if we go from A to B, we want to find the length of a certain curve that goes from A to B. So we're going to do the same thing that we normally do. Divide up into little segments. And then what we're going to do is approximate each of those little segments by a line segment. And if you do enough of these, you can get kind of as close as an approximation as you want to get. And so that's basically what's going on. And then there's, again, you can follow the derivation here if you want. Basically, a little bit of work has to be done here to get to this formula. And actually, you have to use the mean value theorem back from Calculus 1 to do this derivation. But in the end, we get everything set up, and you end up with an arc length formula for y equals f of x. This works as long as f has a continuous first derivative on the interval. We need that because that turns out to be in the formula. And then the length of our curve from A to B, you just integrate from A to B, the square root of 1 plus f prime of x squared dx. That is a pretty straightforward formula to find arc length. Now, we'll come back later in Chapter 10 and we'll talk about expressing curves parametrically, which will be a little different. And then in Calculus 3, you'll find arc length again, with a different formula for parametrically defined equations. Okay, I'm not going to go through the rest of the examples here. You will see that you also have a formula if you have something defined in the form g of y instead of f of x. And they even do example 6 here of a reason that you might need that. This particular one, we cannot use our first formula with f of x because we don't have a continuous derivative here because we have a vertical tangent line at 1. But if you switch things and do this function as a function of y, you don't have any such problems and you can actually work this out. So that's something they go through in example 6. Okay, so again, just a couple formulas really come out of this section. It's pretty clear what arc length is. Setting it up, again, if you want to read through that, you can. But setting these integrals up is something that, we're pretty used to how this approximation and stuff works. And then just can you work the integrals out? That's pretty much what this comes down to. Okay, we're now moving to section 6.7, and we're going to look at a few things here. Some physical applications. These are supposed to be problems from physics and engineering. We're going to look at mass, work, pressure, and force. And the first thing that we're going to look at is mass of a one-dimensional object. So we're thinking about a thin bar or wire on an interval, and we have some density function for that thing. We can find the mass by just integrating the density function. So you have a problem like that in your try problems for tonight. So again, you just kind of plug in the density function, integrate on the region that you're given, or on the interval that you're given. Voila. Work. If you have a variable force and you want to find the work done by a variable force and moving an object along a line in the direction of the force, we just integrate, again from A to B, and this time f of x dx. So we're integrating the force. They do an example here with Hooke's law. Again, you can go through this example. It's probably a good idea. Example 2 here is very similar to a problem I give you in the try problems for tomorrow. So I'd encourage you to look through this example 2. In fact, you can just pause the video and kind of look at it now, how they set things up. Now things do get a little more complicated when we start to look at these things that they call lifting problems. So they give here a procedure for solving lifting problems, and then go through an example with pumping water, pumping gasoline. Yeah, so example 3, example 4 with pumping water, pumping gasoline. They're using this formula here. There's a little bit of work in figuring out what A of y is going to be, what D of y is going to be, that sort of thing. I think we'll actually do one of these examples in class. And then I don't think we're going to look at solving these force and pressure problems. Well, I don't know, maybe one will make it into one of the group's problems, but I don't think we're going to look at them. You could definitely read through this and read over the procedure and look at example 5 if you so desired. But the main things to get out of this section, just mass of a one-dimensional object, work done by a variable force, including a Hooke's Law problem, and then we're going to solve a couple of these lifting problems. So again, we've reached the part of chapter 6 where we're trying to go a little faster, and we're just kind of briefly hitting a couple of these sections. After this, we have one more left to go. I think you have 6 try problems to do for tomorrow, and maybe we'll get to go over some of those, and I'm going to quit talking now.